uh, like to do, we'll try to get through the presentations. Some of this is mostly discussion. Typically on our December tag meetings, we have more of a discussion on our research projects and the contracts that we have with the different folks. And I mostly wanted to go over where we are with some of those, and then what direction we want to go in the future. So I will go ahead and get started with the bioenergetics proposal. As you know, last year that was not funded by our program. So we didn't have a contract with USU for the bird work last year. So that was absent. So we're looking at asking again this year for funding. So I sent out a proposal regarding that and tried to provide an updated version of that. We're still working through it with some of our internal staff that are making contributions to that and suggestions based on the reason for last year it getting denied. So Mike, I saw that you were on, so I'll give you a minute if you want to provide kind of an overview of that project, and then I'll kind of summarize what DWR was looking for when we were asking for this project, and then we'll just take questions from anybody else, as well as suggestions as far as what you read through with the proposal, and any thoughts that you have as far as the direction that we're going with that. So Mike, I'll let you go ahead and talk. Hopefully that this virtual thing will work for us.
Thank you. Hope everybody can hear me okay. What we're proposing is to develop a bioenergetic model for the Great Salt Lake, focusing on the waters that are used by water birds or ducks, basically the shallow waters. For many years, we've worked on the pelagic parts of the Great Salt Lake where the phalaropes and grebes are. This time we're proposing to look at the impounded wetlands around the Great Salt Lake, the shallow water bays like Bear River Bay. What a bioenergetic model does is it looks at things from a standpoint of energy, particularly of kilocalories. And what it does is Doug Ramsey is joining me on this. And what we're plan to do is to map the shallow waters of the Great Salt Lake, and so that we can basically determine when the lake's at a certain elevation, where is the water that's less than 4 inches deep that the shorebirds can use, how much of it. As the water rises or drops, those areas will dry out, but where is the new shallow water that the water birds can use. We also go out in those areas and measure the biomass of food that's available. That's the hard part, because it takes basically thousands of samples to do that. And if you know how much area is out there that is available to shorebirds that has the amount of water that a particular shorebird needs, and if you know how much energy is being produced, or if it's a standing crop, what that standing crop is in terms of kilocalories, then you can predict that, well, avocets have this much food available along the Great Salt Lake. The other part of it is we then go out and count the number of birds that are out there, how long they're out. Birds basically are turned into consumers of kilocalories. You monitor basically how many birds are out there, how much what they spend their behavior on every day, how much of it is feeding, how much resting, how much walking, how much flying, the cost of those behaviors. And then you basically determine how many day uses avocets there are. If you have 1,000 avocets and they're out there for 100 days, that would be 100,000 use days, which is how many basically days you have to feed a phalarope. And so you can then compare the amount of food that's available in the Great Salt Lake, and you can measure the amount of food that those birds need. One of the great examples of it was at a Forsyth National Wildlife Refuge in New Jersey. They did that for ducks. In that particular refuge, the ducks, they were using black ducks as their surrogate. They found basically, they observed that all the black ducks were leaving by the end of September. They wondered why. When they did a bioenergetic model, they found out basically that by the end of September, they found out, they did an energetic model, that all of the food had been consumed by the end of September. So the ducks were leaving simply because there was no more food available to them. It's not like they were migrating further south. There simply was no more food in that refuge. While it was there, they were happy. When it wasn't, they had to leave. And we're proposing to do something like that for the shallow water wetlands, the impoundments around the Great Salt Lake, so that we can basically predict how much food's available. We'll look at the importance of water in that we can quantify over time if something is impounded today, how much food's going to be available in a month or 2 months, so that we can calculate basically how the food will be generated, how fast it's generated, and how that is impacted by the presence of water. That's probably my 2-minute introduction there.
Perfect. So and as far as the division is concerned, we're looking at management implications that would be informed by this model, because we're trying to understand, especially with the amount of water that's going to be available to some of these wetlands, not only on the impoundments, but in the bays. Obviously, over the last couple of, last several years, Bear River Bay, Ogden Bay, and Farmington Bay have decreased considerably in the amount of water that's available there. That is typically provides a lot of habitat, especially for shorebirds, but also waterfowl, depending on lake elevation. And over the course of the last few years with the drought, that amount of habitat and available forage that should be there for some of these suites of bird species is just a open dirt. So that usually doesn't provide much for food. So we're shrinking the available forage and habitat available for some of these birds. And so I think, as I indicated on some of the proposal, right now our managers have not been able to are not managing based on any empirical data. They are managing more by feel and what they've traditionally done. If they see that an impoundment is not being productive one year, then they typically will adjust that by either doing carp control, drawdown, Phragmites, spraying, whatever they think is going to improve that particular impoundment. but as we reduce the amount of habitat available, just because these bays are drying up, we're trying to get a better idea of whether or not we're providing the resources for these birds. Kind of like Mike said with the black duck, they basically left because there wasn't any food available. Is that happening here at Great Salt Lake for any species of bird? And we want to understand whether or not we can do something in our management strategies to make sure that we cover the amount of or make more forage available for a particular species depending on which one is lacking. And right now we don't have that information. So this is kind of the study that will help us understand that and help not only the state WMA managers to be more efficient with the way they manage, but also duck clubs, federal refuges, and anybody else that would be able to take advantage of this model to help us understand how to hopefully look at Great Salt Lake as a whole and manage it more cooperatively instead of everybody just looking at what they want to see at their particular area. So hopefully that made sense, and it's kind of in its development stages as far as this study goes. And I might just ask Robert Shields. I know you in particular have familiarity with these bioenergetic studies because that's how most of the reservoirs are managed. And if you want to maybe kind of summarize how that's done and why kind of this should hopefully work for our when we do this for the migratory birds, maybe you could give us a little background on how that's done in the reservoirs for the aquatic section.
Yeah, absolutely. I can do that. So yeah, we use the same sort of bioenergetics framework to get at the question of managing populations in a reservoir, specifically forage availability, and we make stocking decisions for predators based on how much forage is available in an ideal situation. Of course, I wouldn't say we do it with most of our reservoirs. We don't have the resources to necessarily do this on that scale, but we do get a lot of great information from the studies we have done. We're currently working on a project at Starvation Reservoir to help manage the walleye fishery and other fisheries in that reservoir. And the way Mike laid this out is very close to what we do. We'll look at availability of forage resources. We will estimate the daily or seasonal need of energy for fish species, and basically figure out how many calories they need throughout the year, throughout the season, to put on a certain amount of growth. And we also will couple that with a predator prey model, and in that way we can say, we've got 1,000 tiger muskie in Joe's Valley. We're not sure if the carrying capacity for that species has been met, so we do a bioenergetic study and estimate that we probably don't need to stock in this next year. There isn't enough resources, there isn't enough acreage to start with, but there's not enough food resources to effectively keep going with any kind of stocking strategy, and we'll skip a year based on the results of the study. In reading through the proposal again, I think, Mike, I think it's in a lot better shape than it was last year. I know the main concern was that it didn't address specific management goals or address how we would change our management practices based on the results of the study. In the new proposal, that's touched on several times. And my suggestion, after reading it again, is that I wonder if it would be useful to illustrate a hypothetical scenario where, we've potentially completed this study, and based on water levels in a hypothetical year, maybe we flood an additional certain square acreage of wetlands to a certain depth, because we know we're going to need to boost the standing crop of macrophytes or invertebrates to sustain the needs in the coming year. I think that's probably my only suggestion at this point, and I'll leave it at that as a suggestion, and you can do what you will with it.
I appreciate that suggestion. I'll make sure I do that.
I mean, you've practiced this in the past. This would be our first swing at utilizing a model like this, but it's obvious that you've done this before I get too far. Lynn, you had a question, so I'll go ahead and let you ask that.
Yeah, thank you. The irony is, of course, is that 3 of the bays that you mentioned are important bird areas. So, a deficit in that ability to serve for habitat values and the bioenergetics is really tragic. I was just wondering, could you review again the cost and the, I guess, the multiple years that this proposal would need? And isn't there money in the legislature for water-related insights and support that could be earmarked or focused on this particular proposal? Because it's just so timely. And I think I said last time we talked about this that it would be an indication of a return on investment to the Utah State Legislature as we talk more and more about water needing to come to the system. Thank you.
Yeah, so let Mike answer the budget question, because he's adjusted that, and I actually don't think that's reflected on the proposal that I sent out, because partly because of the way we do things now, he's moving just so he can get a student in by the time we start this. He's moving his request back to start in January. So I'll let you explain that, Mike, as far as the budget goes and then the cost per year.
Well, what we have done is last year, the problem is, as you all know, the Great Salt Lake changes year from year greatly. And you can't do a study like this in just one year, because you'll match the conditions for that year, but you won't have the variability when you have a drought like this or when you have a normal year. So we want to do it for as many years as we can. Initially, I had proposed to do it for 5 years, but we got pushback that that was too long. So in this latest draft, we cut it to 4 years. What I'm proposing is one PhD student and one of our undergraduate students to work full-time during the summer, half-time during the school year to analyze samples. The real study like this is very labor intensive. You have to go out basically to the same site over time, so that you can see how macro vertebrate invertebrate populations are changing over time. You have to take these samples and go and analyze to see what's there. You're also, I had forgotten to mention that we need to know the bird's diet, which we'll get from the literature. So basically, in the case of, like, let's say swans, where it's pretty well known, they want a certain plant. We know there's going to be 50,000. We know they're going to be here for so long. And the question is, well, are we providing enough food for them? And is the 50,000 swans we have here, is it limited because there's no more food for more? Or if we increase the amount of sago pondweed, could we actually have more swans here? And then if you do that, then there's going to be a payoff in that if you provide more food for swans, there'll be less food for, say, shorebirds like avocets or stilts, and we want to make that trade-off. So we're proposing 48 months. Last year, I got in trouble, what I'll call trouble anyway. I had anticipated that this thing would be funded last year, and I realized by about July it wasn't going to be, and I needed a grad student to start July 1. And so I had recruited a grad student, and I expected for him to start July 1. And then about May, I realized that wasn't going to happen. So then I had to call him back and say, oops, sorry about that. We really don't have funding for you. So we had to seek other alternatives at the last moment. So this year I proposed to start funding January 1, 6 months after. Hopefully we'll know whether this thing is funded, so I can then use the fall, when I know whether or not I'll have funding, to recruit a grad student. It's very difficult for a project like this involving a grad student that has to be recruited to find out a month or two before July whether it's going to be funded, and then try to start this July 1. So we have pushed it back to January, simply to give us more time to find a grad student, and that'll give him more time to get his feet on the ground before everything starts rushing in the spring.
So real quick, to finish up the other question that Lynn had, which was the latest governor's budget that showed that there'd be money appropriated to Great Salt Lake. I'd be happy to let anybody else answer this. As far as I know, and Tim, if he was here, and he may join us later, I think he's actually up at the Capitol now. So he may come a little bit later, and he might have a little better idea here. But from my understanding, the money that the governor was talking about was not specifically identified for research. So that is not something that we can tap into as far as this program goes. So I think it was a lot of money was provided for infrastructure, obviously, like marina dredging or an adjustment in the causeway to help us with the salinity balance. Laura, I'm not sure if you have any more info for this than I do, but that's essentially all I know about monies provided to the for Great Salt Lake.
Hi everyone. You hit it on the head, John. It's not, well, I think the first thing is nothing is set in stone yet. There's no list or priorities necessarily for this money, but it is a lot for on the ground work. But those specific tasks have yet to be identified. But research is not is not listed as a priority, I guess, in this bit of funding, as I understand.
Okay, and that's kind of where as far as I know, I'm usually the last to know anyway. So that doesn't say, Lynn, that there won't be money available. It's just that I haven't heard of anything that we're able to take advantage as far as that goes. So it basically is not a part of any of this study. So, or can't be, as far as I know. So
Can you just provide a quick price tag?
yeah, so we're looking at just short of $500,000 for that 4 years, I think. Isn't that right, Mike?
That's correct.
Yeah, so we're actively looking for those funds now. So if you have any suggestions, you can call me afterwards. Okay, so real quick, I'll go to Chris because she has her hand raised also.
Hi, I've got two questions. They're kind of go in two different directions, but they're both short. So the first one is, as far as the finding the areas that are that depth, is the bathymetry model developed by USGS useful, or is it kind of lose its precision once you get out, into the kind of sub 12-inch areas? And the second question I've got is, particularly like after the first year, which I assume will probably be just getting things organized. It seems like potentially this might be a good project to bring in community scientists, like perhaps dedicated hunters or people like that, to, because it sounds like it could potentially be a pretty, time intensive effort in terms of, monitoring birds for long enough to be able to populate that model. So I'm just curious about those aspects of it.
Yeah, so actually those are two really good points. As far as the bathymetry note is concerned, you and Ryan, maybe, in fact, Ryan, if you're on, maybe you can provide that, because I think a lot of that work was on the more the pelagic portions of the lake. And I think we're probably, and maybe even Laura might know, because I know Buck worked on some LIDAR stuff in some of the bays, and those would be probably what we would have to tap into to understand some of that, what you're talking about as far as bathymetry goes.
So just quickly, I'll chime in. I know that Rob Baskin has bathymetry information for Farmington Bay, but I believe Bear River Bay, he wasn't able to get any, do any measurements in Bear River Bay. So we're totally lacking in Bear River Bay. And then Laura can speak. I know the state's got this great LIDAR data set, and I think the Great Salt Lake Tech team has been discussing how to mesh the LIDAR data with the Rob Baskin's bathymetry data. Maybe Laura can speak to that. I'm a little bit out of the loop on that.
Yeah, it's my understanding that the LIDAR data, it only covers the portion of the lake bed that was exposed at the time of the LIDAR flight. So I don't think it goes down to the elevation that we're at now. So there would be a gap in the Baskin data and then the LIDAR data that we have now.
Yeah, so, and to go along with that, we actually have a person on our program who is working with Intermountain West Joint Venture to help us on a separate project to look at being able to map areas that at certain lake elevations, whether or not those areas have been inundated. So we're trying to, we have several other projects that are not necessarily related to this, but ultimately would be related to it. So we're kind of hitting around it with some other funding and some other projects in anticipation that we'll ultimately be able to feed this into this bioenergetic model. And then to go along with, or the second part of your question, Chris, as far as utilizing other volunteers, we've actually reached out to Janice Gardner, and she might be on the on here as well. And there's another project that may coincide with this bioenergetic study, which is a shorebird. I want to call it a shorebird assessment. Is that? Yeah, it's a population study, and it is an effort to duplicate what Schuper did back in the early 90s, where they looked at all or tried to get a snapshot of what shorebird populations were at the time. And there's an effort by Point Blue to duplicate that. Point Blue and Audubon are putting together a multi-state survey in which we would be able to take a snapshot of where shorebird populations are, trying to identify all the areas that shorebirds are going to be, and then do a one day coordinated survey to help us get a full picture of where shorebird populations are. And that is going to utilize volunteers as well. And so that's being put together right now. We're in the process of informing Point Blue where, and that's what John Neal is doing, along with Ashley and Janice, trying to get volunteers coordinated for this effort to get a snapshot of what shorebirds populations are right now. So does that answer your question?
Mm-hmm. Yeah. Thank you.
And so I know we kind of talked about some of the management implications, and I probably oversimplified that in some respects. And just to give another example of one of the things that we would utilize as managers is we talked about sago pondweed, for instance, growing sago pondweed. Well, we do that in a lot of our impoundments because that's the primary food source for the tundra swans, for most of the waterfowl that utilize the Great Salt Lake. But we don't measure densities of that as well. And there's some questions as far as management strategies goes, as with water manipulation, carp control. How does that impact these sago pondweed densities in some of our areas? And is there a way similar to what you do on range, on understanding what's happening on ranges where you have a burn, and then immediately after you have this regeneration of the grasses, and it provides a lot of forage for animals right after that. And then as time goes by, you start to get this decadent forage, or where the grasses are kind of decadent, and it becomes less productive. And so you try to burn every so many years to be more efficient with your range and make it more productive. And we do this similar thing with our brine shrimp out on the pelagic portions of the lake, where we manage the brine shrimp fishery based on the model that Gary has put together, and try to maximize the productivity of those areas. We want to do the same things in these wetlands to try to maximize our productivity, and we want to understand how to do that. And right now we don't really know what some of these management strategies are actually giving us. So that's one of the other things that we'd like to do, and hopefully help us take some actual measurements so we can identify how that's impacting those impoundments. So hopefully that helps give you an idea of why we're doing this and what we can use it for. So anyway, anybody else have any? Yes, Gary. Sorry.
I'm trying to ask Mike a question. First of all, I think this is great because we don't know anything about the system you're looking at in terms of the overall of the Great Salt Lake. But my question has to do with this. I know a number of the birds are going to be restricted to the wetlands. Are there going to be species that could be forced from the wetlands to use the bigger portion of the Great Salt Lake if food becomes reduced in the wetlands? And if so, are you going to be monitoring the birds to see if they move to use the open water or the shorelines of the open water of the lake?
Well, if we look at shorebirds, for instance, other than phalaropes are a shorebird, but they have a unique ability to move their feet to cause upwelling. So they can feed on invertebrates that are down a half a meter or more. Most shorebirds cannot. They can only be in water suitable for the length of their legs, which varies from species to species to 1 inch up to 5 inches. And so they could move to wherever the water is that's the appropriate depth for them, but they can't use the pelagic areas. That's just beyond their ability. If we don't have the amount of forage for them here, if they run out of food, unlike the refuge in New Jersey, they're going to be in a world of hurt because we're sort of an oasis out here in the desert. It's the same problem we have with grebes, as you're well aware, Gary, that we have a couple million grebes that are on the Great Salt Lake. And once they're here, this is it. If we run out of food, if they run out of food, they can't fly. There's nowhere else for them to go. This is the greatest wetland in the western U.S. If we run out of food, there's just no place else for them to go. And that's true for a lot of these shorebirds too, that the Great Salt Lake has a great amount of potential habitat for them. But if we can't provide food for them here, they could move to a much smaller refuge further down in the flyway, but it just won't have the amount of food that they're going to need.
I understand what you're saying, Mike, but what I'm wondering about is if some of these shorebirds that normally are restricted to the wetlands and the lake level drops and now it's only 5 inches or 2 inches of water above a microbialite, are they going to move from where they normally would be in the wetland and feed on, say, brine fly larvae on the microbialites? And would you be measuring that?
Yes. Doug Ramsey will be basically preparing maps that are going to show the depth of water that's within, say, 2 inches of depth or 4 inches of depth, and how that changes as lake levels drop. And at levels now, a lot of microbialites are out of water or very shallow water, and these shorebirds that do not normally feed on microbialites will certainly move out there. if that's the only thing available. And it's probably pretty good habitat, but what impact that'll have on the microbialites themselves is unknown.
So and this is something, Mark and I have been flying these midwinter flights, and this is just observational again, and I don't know, maybe the data would, if you look at it from previous years, but goldeneye, when Josh was here, we had the highest concentration of goldeneye, wintering goldeneye anywhere in the interior U.S. At least from what I'm seeing, that population has dropped way off. And I don't know if it has anything to do with exposure or the salinity. Maybe it's not efficient for them to be on the lake, and they're, the buoyancy, they're having a tough time because of higher. I have no idea. But at least observationally, I have seen less goldeneye on the lake, but I have seen a huge increase in shovelers out on the lake and clear out on the pelagic portions of the lake. Tens of thousands of shovelers. And Thomas, maybe your crew's on the lake, or you're seeing more waterfowl out there. But at least in the flights, I have not seen the numbers of, and I know you talking about shorebirds, but this, and maybe these are the least desirable species of ducks when you're talking about shovelers and goldeneye. But though there's a complete shift there from what I've seen in the last few years, not. And maybe it's been a gradual shift over time, but we used to have a whole lot more goldeneyes, far fewer shovelers, and it seems to me they're feeding on cysts because they're out on streaks, but they're everywhere on the south arm of the lake, shoveler-wise. And so I don't know if there's some change there, but they don't have what they used to have available to them in these bays and in the wetlands, apparently.
Well, I'm just wondering whether that these shorebirds are spending 100% of their time in the wetlands, and as the lake level drops and exposes the microbialite, you might find that 25% of their time now is spent on microbialites out in the pelagic, what we call the pelagic portion of the lake. And thereby you might have to track the movements of these birds.
Right. So, and that brings up another, talking specifically about shorebirds, I've seen a huge amount of avocets clear on the west side of the lake as well, late in September. On our flights there. And it seems like they concentrate over in the bombing range and along where the water is flowing through, or if there is flow through from that culvert, or just over by Gunnison Island back towards the causeway. So again, there's another group of birds that are shifting for some, and why be over there where there is no fresh water unless that's the most productive area as far as food resources go. And so those things are shifting, and it could be that it's already happening. Yeah.
I'm just saying, keep your eyes open for this.
Right. I mean, we're noticing that a lot more. We're also seeing on occasion we get phalaropes in the north arm, and I'm not sure if they're feeding on surface brine flies because of them lighting on exposed microbialites that are covered in salt, but it provides a landing place for a lot of these flies, and that would be a food source. That's all I can figure, but we actually don't really know that for sure. And I think you don't, we wouldn't assume that these shorebirds are actually using a lot of the impounded wetlands exclusively. I would say they're also provided a lot of habitat in those bays if they have water, and that's continue to be reduced. So it's probably more important to understand what that impact is, because I think you had a lot of shorebird habitat out in those bays that is no longer there because there's just no water, and it might be more critical to manage for some of those in some of the impounded wetlands where you can manipulate the water level, and if we know that there's a species that's being impacted because there is no habitat available now. So,
but it sounds like from your observations, John, that the shores of the pelagic region of the lakes, could be important. So is that part of the study that Mike is proposing, that they would at least look at that to see if there's a shift?
no, and I think that's kind of what you were getting at there with that. So right now, no, because that's at least we're mainly focused on what is being provided with the wetlands, the impounded wetlands, as well as these 3 different bays, because each one of those bays are differentiated by salinity. And so you can't categorize those in any way as being the same. So we have to differentiate those, and we also have to differentiate the impoundments in all those different bays as well. And so that's the difficulty that Mike's going to have as far as sampling size and being able to cover those, because there's also different variables, substrate, a lot of different variables that have to be taken into account. So the amount of sampling that needs to be taken or done in these areas, that's what's going to be the high cost. Excuse me, the high cost. And that's probably why Chris was asking about utilizing volunteers, because there's no way to do this with a student and just the work that Mike and a couple of students would do. So we're going to have to chip in as far as the division goes, as well as utilizing volunteers, which is why we wanted to try to overlap that shorebird work that or that effort that's being conducted flyway wide. If there's a way that we can utilize volunteers from that on this project, then we certainly want to do that. So,
John, I don't know if it's helpful, but if y'all need any sort of writing about microbialites or any of those angles or discussions, we've been doing a lot of that. I'd love to help you with that. So just let me know.
sounds good. Do you have some money that is hiding that you could provide to?
Well, yeah, there is my Aunt Patsy.
Okay, Aunt Patsy is going to be one of our cooperators. And Heidi, did you have a question also?
I just wanted to comment on the importance of listing the species of shorebirds you're speaking of, using the fringes near the open water out in the more saline habitat is very different. And you're not likely to see some species out on the exposed microbialites because they're typically known to probe in soft sediment. So it just, as you go down this path, it'd be important to characterize habitat, which it sounds like you will be doing.
Right, and the other good thing that is in our favor is we have a lot of monitoring data from the surveys that we've conducted since the 5-year waterbird survey that gives us ideas of when these different species arrive and how long they typically stay here, and also how those locations have changed with the lake elevation. We just don't know enough about what food there is available to them and how the water levels impact that. I think, and those are the questions that we're mostly hoping to answer. And obviously we'll have to look at some of those other parameters when we're picking our sites. Is there any other questions? And I know I had slated quite a bit of time for this. I just wanted to make sure we adequately covered this, especially since we provided the proposal. And if there is, I don't want to just limit it to this meeting, but we need to get this proposal finished up in the next couple weeks so that it can be submitted to our director's office so they can give a thumbs up or thumbs down based on what it provides for the division. So if you have questions, let's keep going over those. If you have questions that you're not sure about and want to ask, or any suggestions as far as input, just like what Heidi shared there, please do that. Also keep in mind that this is going to be a big project. It already is. So if you're adding to it, maybe we'll add to it in subsequent years, but right now I just want to get started on this so that we can get some actual data and help our waterfowl managers with their areas. So any other questions? Yes, Chris. Chris?
I'm on mute. Sorry about that. Did you send that proposal around in a previous email or?
Yes, I hope. Did everybody?
I didn't.
It was for this. I included it on this email, the second email that I sent out with the agenda and this. It should have been.
It was attached to the Google Meet invite.
Yeah.
Google Calendar.
Oh, okay.
So it wasn't on the original invite. We do everything.
Okay, I'll have to find it if I can.
Okay, if not, I can send that out to you after the meeting. I can send it to everyone again. So
Yeah, that might be worth it.
Yeah.
I'm seeing that the invite has the notes from the last meeting, but I'm not seeing it.
yeah, that was the original email that I sent out. Then I sent a subsequent email with this link to join via the virtually, and it should have been attached to that one, which I sent Monday.
Okay. Yeah, I'm not seeing it. If you can resend it, that'd be great. Appreciate it.
Well, that was completely unhelpful if nobody got that. So I will send that to everyone.
Also attached to the Google Meet, go to the info button at the bottom right. You can download it from there. Oh.
Yeah, John just said that if you go to the info button on this, where you're at right now,
Okay.
and you can download it from there.
Okay.
And most of us don't look on something
Yeah.
that says is hidden as an info button.
That's
Hmm.
regardless. I will resend that after the meeting to everyone with just a regular email, since that's easily far easier than dealing with one of these emails.
Okay.
I apologize for that. I probably should have, I just didn't want to inundate everybody with too many emails. 2 seemed like too many in the first place. Sorry about that. Okay, any other questions as far as the bioenergetic study goes? Okay, well, then we'll go ahead and move ahead. And Ryan, I don't know if you had a presentation available and if we can figure that out.
Yes. So what I'd like to do is just briefly go over our work plan that we're acting on right now, the FY 2022 work plan, so people can see the costs and the kind of work that we want to continue. And then we have a presentation that'll kind of show how we're using the data that we're collecting as part of our work plan with the ecosystems program. So that's kind of what I want to do, if that's okay with you, John.
Yeah, that'd be great. And I want to also emphasize that we want to do another re-ask for expanding the nutrient work. And so for this upcoming fiscal year. So again, I want to try to make sure that that is also something that the TAG is aware of, because that was also cut last year. So I want to make sure that we follow up with that, because I think everyone realizes that the nutrient work is something that is extremely important here. So if that's not part of your discussion, add it to it.
Gotcha. All right, well, let's just start off by looking at our work plan for the current fiscal year. So hopefully you're seeing that. You're seeing are you seeing that? It's kind of the budget table for the work plan. Is everybody seeing that? Great. Okay. So on the current fiscal year's work plan, we have 2 tasks. Task 1 is for a continuous discharge station on the Goggin Drain, one of our surface water inputs to Great Salt Lake. And then also for periodic measurements, discharge measurements at the Bear River Bay outflow at the causeway. You can see the total costs associated with that, $23,500. The second task is for the nutrient sampling and analysis. And this is the basic data collection program for nutrients that we've had going on since about 2011, I want to say. And the cost for that is $100,000 essentially. So a total cost of $124,000. And then you can see the Division of Wildlife Resources cost share at about $72,000 and the USGS cost share on this at about $52,000. And a little more information on what we're getting from these funds. It's easy to understand the discharge, the strain gauge at Goggin Drain, the periodic discharge measurements at Bear River Bay outflow. In addition, when we make those, one thing you may not know is when we make those periodic discharge measurements at Bear River Bay outflow, we also generally collect nutrient samples. And so this helps us understand nutrient loading from the Bear River into Great Salt Lake. So without the money from the Wildlife Resources to do the discharge measurements, we would be very hard pressed to get meaningful information about nutrient loads. So and then the Goggin Drain, same thing. There's nutrient sampling that happens at that stream gauge, and it helps us with nutrient loads as well as just the water balance on the lake. So task 2, which is the much larger cost, includes nutrient sampling at 4 river inflow sites. So that includes the Goggin Drain, Farmington Bay outflow, Weber River near Plain City, and then the Bear River outflow that I just discussed. Also, we sample for nutrients at the 2 railroad causeway breaches. So the old breach over by Lakeside on the west side, and then the new breach. And the new breach is actually, because we have bidirectional flow, that's actually a set of nutrient samples that are collected there each visit. So, this fund, these funds that are a part of this agreement are collecting some of our most basic information for Great Salt Lake. Generally, with this agreement, this gets to what John was just remarking about. There's an additional task or 2 on here. And those add up to about an additional $82,000 total on this agreement that you're not seeing here for the current year. So that was cut to kind of help with drought budget issues at DWR. And so going forward, task 3 for us would be to pick up on the nutrient mass flux work that Christine and others here have been working on. And that's a more complicated exercise than just nutrient loads coming in from the stream flows, or this is getting at how are nutrients moving from sediment to the deep brine to the upper brine, and so on. So and also it tries to get at flux rates between those nutrient pools. And so going forward, we would be looking to start that work back up, but we haven't thought about what that would entail just yet, because we're still wrapping up the initial phase that we initiated a year ago. So we would like to wrap up the report for phase 1, we call it, and then be able to insert an additional task in here to continue that work. So since John said we would be looking to replace these funds, about 82,000 to this agreement, then we're going to be talking internally about how we want to push forward on that nutrient mass flux work, and then share that out with the tag and get your feedback. So I'm not prepared to talk about that right now. Are there any questions? So at a minimum, we're obviously we're going to be pushing. We want to push forward with this basic data collection that you're looking at right now. Are there any questions on the DWR work plan for the current fiscal year?
So Ryan, when do you think you'll wrap up that phase 1 and you'll have a better idea of how you might want to go forward with the research on the nutrient cycling, nutrient flux?
Yeah, I think it's going to take us a while. Quite frankly, we've had to divert our attention more to salinity issues on the lake these last several months. So I think we're, a good 6 months away from having like a draft report for phase 1. So we may not get, anything in the FY 2020, or excuse me, the FY 2023 budget for resuming the nutrient mass flux work. But we might be able to get far enough along here in the next few months to put a good productive additional task in here, but no promises.
Anybody else have any questions? And if you're able to do that, Ryan, we'll do what we've done in the past and just and kind of what I've done or attempted to do with the bioenergetic study, because since these are newer projects that we're trying to get started, I will send that out to the tag and get input from you all, and then we'll proceed and try to fund what we're allotted to fund as far as the division is concerned.
Yeah, and I can say in regards to phase 1 for the nutrient mass flux work, we're very close to getting a data release wrapped up that includes kind of all this fantastic data that Christine and others collected out there to get at these flux rates out there. So that's coming soon, and then and then as far as drafting up the interpretation, that's where it's going to take us a little bit of time. But we'll think about task 3 over the next couple months and try to get something put together. What the other from my perspective, the other potential issue for us is matching funds in FY23. We'll have to look where we're at. People may not be aware, but the amount of match that we get each year to bring to programs like this is pretty much a fixed amount. It hasn't really increased over the years, and there's a lot of demands on our matching funds right now, just due to the drought and other issues in Utah, all the growth that we're experiencing. So we're gonna have to take a close look at the match that we'll have available as well.
All right.
If there's not any other questions, I'm going to move on to the presentation.
Let Thomas have one other.
Sorry, Thomas.
Yeah, John, I'd like to be on record for two things. I think that Mike's proposal and Mike's work is important for us to gain a better understanding of the wider Great Salt Lake ecosystem. I'd like to be on record with that. I think, secondly, I want to be on record with regard to the nutrient flux research. I think it's extremely important. And I think we need to keep pushing forward with that research. Just some of the initial data that we saw from Christine, where we could see how much of the nutrients were actually in that top layer of the benthos. I don't think any of us had an idea how significant that was. And just this work is already shedding some light on that. And I think we'll need to continue to do a lot of that work to understand what goes on with nutrient cycling. And I think it could become even more important as the lake is shrinking and the volume of the lake is getting smaller. What happens with those nutrients in terms of are we getting a higher nutrient concentration or are we not, and how that could affect the Artemia population and the other, the brine fire population, the bioherms, and so on. So I think it's very important work, and I'd like to be on the record that I think we need to continue to find the funds for that work.
Yeah, it's obviously going to be more and more critical as the lake continues to shrink to understand what's going on. Our cushion for making any mistakes or not understanding it is going to be inexcusable.
Yeah, one of the main drivers of the ecosystem. So we've got to understand that.
Yeah.
All right, Ryan, we'll let you continue with your presentation.
All right. Okay. Well, hopefully you see our lead-in slide here for the Great Salt Lake Tide meeting for today. And we have a team. We have a large team here devoted to a lot of the work on Great Salt Lake. So I've listed the folks there. It's a large team effort. And then I would just say that this team extends to you guys and then to John Luff's group as well, who actually collect monthly nutrient samples in the main body of the lake. And that's no small task. And those nutrient samples, then we take them and send them to our water quality lab. So the team is USGS and much larger. Many of you who are on the call. So we thank you very much for the opportunity to work with you all. We're going to talk about lake, kind of our usual lake elevations, and then we'll look at inflow discharge data. We'll look a little bit at the water quality data that we're collecting, both mostly from the inflows, or excuse me, in-lake water quality data today. And then we're going to talk in a little more detail about salinity and salinity trends on the lake, just so that everybody's aware of the situation we're facing out there. Okay, well, starting off, we'll look at our data for the Saltair gauge on the south end of the lake. I'm showing a year's worth of data here. These are average daily values. As of December 13th, we were at 4190.6. That's down about 1.5 feet from a year ago. And probably everybody's aware, but we did hit a new historic low in October. And again, we're talking average daily values or daily mean values. We hit on October 18th, we hit 4190.2, and that's the lowest daily mean value that we've ever recorded on the lake. And we have a record at this site going back to 1847. So that new historic low is about a foot, a little more than a foot below the 1963 record. Looking at the plot, you can see we've rebounded a little bit since we reached that low. And we've remained steady for the last month or so. I mean, remarkably steady out there. So You can see, I think we benefited quite a bit from the moisture we got from some thunderstorms in the summer and then early season snowfall, etc. So the lake has come up a little bit and we're holding steady. So that's great news. We're going to look for it to increase, right? Quite a bit more. We're all doing what we can to bring in more snow. Just to give you all a sense of the seasonal increases or decreases that we've seen since about 2011 at our salt air gauge, I created this plot to help us understand that. And on average, the seasonal increases due to runoff, etc., kind of where I'm highlighting here on the plot for the 2013 area. 2011, we had a great rise in lake elevation. But on average, we're increasing about 2.2 feet over the period of time I'm showing on this plot. And then the seasonal decrease through the summer months, the warm months, and into winter, on average is around 2.3 feet. So, from 2011 on, we're kind of losing a little bit of ground there. And then this season, we lost a lot of ground. We only had a seasonal increase of about a foot, and then we dropped almost 3 feet during the warm summer month. And you can see that's kind of where I'm highlighting right here, where we had this small seasonal increase and then this rapid decline. So that's just to give you a sense of how the lake's behaved since about 2011. For our gauge on the north arm, the situation is very similar for this past year. We didn't have much of a rise during the runoff season, and then we had a significant drop. And as of December 13th, we were at 4190.1, and like the north or the southern gauge, we're down about 1.5 feet. We have the historic low was actually measured at this site in September of 2016, and that's when the culverts were shut down and they were constructing the new breach. So no water was making it into the north arm essentially, and so that's when we achieved a historic low on the north arm. So we didn't get too close to that historic low this year. So that's the situation for the north arm. Okay, and then just as a reminder of where our monitoring sites are. So we're getting continuous discharge data at what I'll call the old breach, also periodic discharge information at the new breach. And we have discharge information for Bear River Bay. We also have discharge information, it's not shown on this map, for Bear River Corinne, which is upstream. We have discharge for Weaver River, Farmington Bay outflow, Goggin Drain. And these sites shown with the yellow squares are also sites where we have nutrient information, nutrient sampling happening. Obviously, as we've discussed, this information, the flow data, the nutrient data that we're collecting, these are fundamental to understanding Great Salt Lake in terms of water balance, salt balance, nutrient balances. Also shown in this map are the open lake sample sites. There's 4 of them. These are the sites that are sampled every month by John Left and his group. Okay, well, just to give a feel for where we're at, up for the Bear River. So we look at the Bear River gauge near Corinne, Utah, because we have a stream gauge there that measures flow continuously. So we can have good numbers for total volume of water passing that gauge each year, etc. And showing data from 2006 out to the end of 2021, and these are water years. So I have volume in acre feet on the y-axis, and so for 2006 we had approximately 1.2 million acre feet represented by this blue dot passed by that gauge in 2006, and so the dashed gray line is kind of the average annual volume passing that gauge from 1950 to 2019. All right, so then we can see what's happened since 2006. Most of these years, water years, we've had flow volumes passing that gauge well below this average line, with the exception of 2011 when we had a great water year and the South Arm actually came up 4 feet plus. We also had a good water year in 2017. So these were 2 water years where we were above that 1.2 million acre feet mark. But otherwise, we've been well below. And then I'll just point out 2021, where we were we had a dismal water year at this site, where we were around, or just above 400,000 acre feet, as opposed to, you know, an average of around 1.2 million acre feet. How are we doing the current water year? So that's beginning October 1st of this year. That's represented by the dark black line on this cumulative flow plot. So on the y-axis, we have millions of acre feet, and then we have the water year represented on the x-axis. This yellow line is the lowest observed cumulative flow at this site, which was in 1992. The blue line is the highest observed, which is in the 80s. And then the green area you can see on the legend kind of represents, you know, a normal or average-ish condition. So for the current water year shown by the dark black line, we're below average. This looks very similar to what happened last year. So this is where we want to start really paying close attention to this Bear River gauge at Corinne and the cumulative flow at this site. It's critical for helping Great Salt Lake water levels recover. So this is where we're at right now. Just briefly, so we go downstream to the causeway and make periodic discharge measurements at the Bear River Bay outflow to the lake. And I'll just point out that we had no observable flows at this site after April of 2021. I'm just talking the recent history here. So we were pretty much no flows from April, you know, late April through early October. So you see these zeros representing late April. And then on October 27th, we measured 1,210 CFS in response to some of the great storms that we had. And then most recently, we measured 822 CFS. And these numbers are pretty similar to what we were measuring at the Corinne gauge. So so we are making these periodic visits to this Bear River outflow site, and nutrient samples were collected concurrent with these discharge measurements. Okay, now the Weaver River. So this is the same type of plot we looked at for the Bear River Corinne. So we have volume in acre feet on the y-axis. You see the dates along the x-axis for these are water years, and then the average volume passing this gauge from 1949 to 2020 was on the order of 300,000 acre feet. And if we come out to the most recent water year, the end of 2021, we did very poorly. So we were below 100,000 acre feet at this site. And you can see, looking back to 2006, we've only had a couple of years where we were above this average value. It's very similar to the Bear River. So this is the next most important inflow for Great Salt Lake in terms of just water, and we need to pay close attention to the flows on the Weaver River. And for the current water year, the cumulative flow in millions of acre feet is shown by the dark black line, and you can see again we're just on the edge of that 25th to 75th percentile area that's shaded green, kind of, you know, what we consider like a normal flow area for cumulative flow. So we're just on the boundary of that. So we're not off to a great start on the Weaver River at Plain City as of yet, but this is another gauge we'll want to watch very closely as we get through the water year. And then quickly we'll talk, here's Gog and Drain, and this is the stream gauge. This data is based on the stream gauge that the Division of DWR pays for or cooperates with us on. And here's the average volume passing that gauge, represented by the dashed line. So on the order of 175,000 acre feet. And then the blue dots represent the water year volumes. In 2021, you can see we were well below the dashed line. And we've only have a few water years where we're above the dashed line. So, you know, just this information is just, you know, explaining why we're in such a hole on Great Salt Lake. That's kind of the essential message here. And for the current water year, represented by the dark black line on this cumulative flow plot, we're doing better at Gog and Drain this year, and that's got to be due to the moisture that we've had in late summer, fall. So things are looking much better for Gog and Drain right now. Let's just keep our fingers crossed that we continue that through the rest of the water year. And then finally, Farmington Bay outflow, we can see the average for 2004 to 2020 in terms of volume is just above 250,000 acre feet. In 2021, we were dismally below that dashed gray line, around 175,000 acre feet. And it's important to note, some people thought this may have been the worst year like ever that we've seen in Farmington Bay outflow in terms of cumulative flows. It's actually not. We've had worse years, but this was one of the worst. You can see in 2018 we had a very bad year in terms of flow volumes at that gauge. I don't have a current cumulative flow plot for this site, as we're working to estimate a little bit of data that we weren't able to get due to equipment failure. So maybe I'll have that for us at the next meeting. Moving on to this simple question. What would it take to raise the lake 4 feet? I personally would love to see the lake raised 4 feet, because I think if we get a 4-foot raise, we're going to likely not be in record low territory again next, late summer or October of next year. So I personally am hoping for at least a 4-foot increase this year. So what would it take? Well, based on Rob Baskin's bathymetry information for the north and south arms, to raise the lake 4 feet from where we're at now would take about 2.5 million acre feet. That's a lot of water. I think like Deer Creek, is 300,000 acre feet. Maybe this is an enormous amount of water that it would take to bring this Great Salt Lake up 4 feet. And when we look at the combined inflow volumes from the Bear River, Weber, Goggin Drain, and Farmington Bay outflow back to 2005, and again, these are just showing water years. So this is the combined volume from these rivers. You see that we've only had a couple of water years where we've gotten enough water, the kind of water that we need to raise the lake 4 feet. So 2011, we had a fantastic water year. Over 3.5 million acre feet came into the lake. 2017 was another good water year where we were just over this 2.5 million acre feet mark. So so out of the last 15 years, we've had a couple of years where we could bring in enough water to this lake from our surface water inflow sites, these guys, to get us, maybe a 4-foot rise. This is just to help give you an idea of potential targets if you dream of such things at night like I do. So fingers crossed for about 2.6 million acre feet. We're off to a good start. This was a good storm that we just had. Okay, now we have the new breach on the lake, where we're making monthly discharge measurements. We've been doing that since 2016. We have many other sensors installed at this lake that are all trying to get at developing continuous discharge information. And we're working closely with Utah State University because they are developing a flow model at that site. But in addition to just monthly discharge measures, we have a resistivity sensor string at this site. We're still working on getting this resistivity string working. This is pro bono. USGS, we're just doing this to see if we can make this work. If we have resistivity at many depths in the water column there, that will help with salinity mass balance calculations. It will also help resolve north to south. There's bidirectional flow at this site, so this will help us resolve bidirectional flows in more detail. So that's the kind of information that we're gathering, or just a little sampling of the information we're gathering at the new breach. And then in terms of our monthly discharge measurements, where we have this great record going all the way back to 2016, the plot looks like this, where we have discharge in CFS on the y-axis, time along the x-axis. Blue circles represent water moving from south to north. Red circles represent water moving from north to south. And also shown on this plot is the elevation difference between the Saltaire gauge and the saline gauge. Those are the two string gauges where we looked at that data at the beginning of the presentation. So that's shown by the gray line. And so the higher this gray line, the higher the south side of the lake is relative to the north. And so you can see, looking at just the most recent data out here, which this was collected earlier this month, by the way, this where you see the 178 and 898, that's cubic feet per second for each of those. The head difference is at about, I shouldn't say head difference, I should say elevation difference of right now is where it is about 0.5 feet. So the south arm is about 0.5 feet above the north arm. And we have 898 CFS moving from south to north and 178 CFS moving from north to south. And we have seasonal signals in the data, no doubt, that you can see here easily. We're at a point now where we start to see the south to north flows increase and relative to the north to south flows. So we're going to look to see a continuation of this trend as we bring more water into the south arm, where these south to north flows are going to continue to increase. And again, this data right here, very critical for the modeling effort that USU is working on. Okay, and then just a little bit of a rehash. We've got the inflow sites. We're doing the nutrient monitoring at these sites. So there's 6 sites. We sample those sites approximately every 6 weeks, and we've got this data set going all the way back to 2011. In addition to those inflow sites, if I just back here, I'll just back up again. The map is important. You can see the inflow locations with the squares, orange squares. And then we have the open water sites. And again, that's with John Luft and his group. They're sampling 4 sites on the lake. They're shown with the purple circles. They sample at 2 depths, so a shallow depth and a deep depth. This happens every month. It's an enormous amount of work. And then those samples are measured for nutrients. We also use the water that they bring back to measure density and estimate salinity from that. Now that nutrient data goes right into papers such as the one Dave Naff's published in 2015, which was a nutrient mass balance for the south arm of Great Salt Lake. So he showed what was coming in from the inflows on a monthly basis and how nutrient masses in the south arm were fluctuating on a monthly basis. So that's a paper he published back in 2015, and the data we've collected since then is going to be used for an updated report. That's going to have data from 2015 out to 2020, maybe to 2021, and we'll compare that, the more recent data with the data that David published. And anyway, this work is ongoing with our investigation section here in Salt Lake. All right, so it's important that we look at density and salinity right now so everybody understands where we're at on the lake. So here I'm showing density, and I'm showing density for 2 sites, 2565 and 3510. You see the map on the upper right showing the locations. So triangles are shallow water samples from those sites. Green is for 2565, blue for 3510. Circles are deep samples from those sites. And the same thing, green is 2565, blue is 3510. So we have density on the y-axis, and we're also showing Great Salt Lake on the second y-axis, Great Salt Lake elevation at Saltaire, pardon me. That's shown by the gray line on the plot. So you can see Great Salt Lake's elevation going back to 2011 over time, and we're all familiar with what's happening with the most recent elevation data out here to the far right with this tremendous decline. Well, with this tremendous decline in lake elevation, the south arm, we see an uptick in density at both 2565 and 3510 in the shallow water until the most recent samples that we've collected, where we see our triangles are kind of leveling off. It's pretty clear at 3510 where you see 2 blue triangles from a couple sampling events. These are less than. This shows a slight decline in density at this site. At least the most recent data are showing that. And then at 2565, a similar story. We had an increase with our green triangles, and then a decline beginning a few months ago, probably related to water coming in from Bear River resulting from many of these storm events that we had. Most recently, there was a slight uptick in density at 2.565, but we fully expect that this is going to level off as well. And, in the outgoing months, we want to see these values start to drop. So we use density data, at least density data up to 1.14 grams per cubic centimeter to estimate salinity using the equation of state that Dave Knapp's published for the south arm of Great Salt Lake. And so we have salinity in grams per liter from the equation of state shown on this plot. The blue circles are deep samples collected at 3510, and then the blue triangles are shallow samples collected at 3510. And like the previous plot, I'm also showing Great Salt Lake elevation with this green, or excuse me, the light gray line on the plot. But let's just focus on the more recent salinity data for 3510. It looks exactly like the density data where we peaked, and now we have a couple of values that are actually a little bit less than the peak salinity value. So again, this is good news, a slight decrease in salinity at 3510. And then for the deep samples at 3510, there's a gap in the salinity information because our density values actually exceeded the range that Dave Knapp's used to develop the equation of state. So we don't want to use the equation of state to calculate salinities using such high densities. But more recently, the deep brine layer we've seen has eroded at 3510 and is disappearing. And so we're getting lower density values in the deep water where we're able to calculate a salinity value. So for those who are nerds and sample Great Salt Lake a lot, this is kind of a significant thing to see the deep brine layer at 3510 erode the way it has. And then, it's the salinities are much less at depth than they were previously when the deep brine layer was robust and thick. Okay, now Christine is going to show a few slides showing kind of salinity, more information on salinity, and it's very important when people think about management implications for Great Salt Lake to kind of understand the salinity trends on the lake. So I'll let Christine take over, but I'm going to run the slides for her. So Christine, take it away.
Great. Good morning, everybody. It's good to see you all. We just wanted to share a few slides of some analysis we've been doing kind of in cooperation with the Salinity Advisory Committee and the Brine Shrimp Cooperative to just better understand salinity variability in the lake and kind of how current conditions fit into our historical record. So kind of two main questions of this analysis were, first of all, what would happen to water column salinities if the upper brine and deep brine layers were to mix? In other words, if the deep brine layer disappears and is mixed into the larger water column, what happens to our salinity concentrations? And then a second question was to just try and understand salt mass in the south arm and how that's been changing over time. So next slide, Ryan. So just to give you a sense of how we approach this, we're using density data collected by USGS and also the Great Salt Lake Ecosystem Program, the monthly samples that you all collect. Those data were used, the densities in the upper brine and the deep brine layer at 2565 and 3510, along with estimated volumes of upper brine and deep brine layer through time to just try and put it into a simple mixing model to understand how salinities would change if the water column were to completely mix. And so next slide, go to that. This is just to give you a sense of how those salinities might vary if the water column were to mix. So this is for the period after the new breach opens, after 2016, at the end of 2016 to the present. And this plot is showing salinity on the y-axis over time. The green symbols and dots represent the mixed, what we would predict would be the mixed water column salinities. And then the blue triangles are observed. And then on the second y-axis on the right, we're showing just the difference between those two and how much of an increase would we expect. And so on average over this 5-year time period, we would predict that if upper brine and deep brine layers were to mix, we would estimate about a 5 gram per liter increase in water column salinities. But it's important to note that that varies through time. As you can see, that gray line sort of is variable, changing anywhere from 2 to maybe 7 grams per liter. So it really depends on the lake conditions at any given time about how much we would expect salinities to increase, but on average about 5 grams per liter. And I'll just say that the Brine Swim Cooperative also did sort of an independent analysis of their data and looking at this kind of idea in a similar way. And I'll just say that our estimates are in the ballpark, which is really encouraging given that we each have independent data sets, independent analysts and analyses. So that's encouraging. Okay, next slide, Ryan. And then we also wanted to begin to understand salinities and how they vary through time. And so this plot shows observed salinity concentrations in the upper brine, that salinity is on the x-axis, and then the Gilbert Bay or South Arm water volume is on the y-axis. So just trying to understand how salinities vary with changing lake conditions, lake levels, and lake volumes. And the color coding represents sort of different conditions that have been present in Great Salt Lake. So the purples, the dark purple represents the condition where the pre-New Breach condition, where we had lakeside open and we had culverts operational through the railroad causeway. And then the light purple is 2015 to 2016. That's when those culverts were closed. So North Arm and South Arm were separated, essentially, no flow exchange, no water exchange. And then the green, light green represents 2017 to 2020. So that's after the New Breach opens up to 2020. And then the dark green represents our last water years, 2021. And then in addition to these data, we've added on some theoretical, what we call isomass lines. And these are basically a conceptual experiment of, like, say, what if we had a fixed mass of salt in the South Arm? And in this case, we're ranging from 900 megatons to 1400 megatons. If we had a fixed mass of salt in the South Arm, how does the concentration of salinity vary with varying lake volumes? And so you can see that with higher lake volumes, kind of in the upper left, we would predict lower salinity values. And then as you move right and down the plot, or those lines, you expect that salinities will increase with lower lake volumes. And so that's just to sort of put our data in the context of salt mass. And kind of what we see, Ryan, if you want to toggle the next slide, what we see is that there have been kind of these shifts over time that are kind of, they're noteworthy. So if we start with this, like, first bullet point, that top circle is highlighting the condition from 2012. And as you can see, it shifted to the left based on the other purple dots. And looking into the data, that represented the condition in 2012. And what's significant about that is that was a year following a huge water year in 2011. In 2011, we had a huge snowmelt runoff and basically unidirectional flow from south to the north. So only exporting water to the North Arm. And this is indicating that there was a significant amount of salt mass that was also exported to the north during that event. Similarly, the second circle after 2000, we see another huge shift to the left to a condition of lower salt mass. So if we estimate those purple dots, they're at about 1,200 megatons of salt in the South Arm. It's shifted after the New Breach opens to about between 1,000 and 1,100 megatons of salt in the South Arm. So huge reduction in salt mass. And that occurred again after the New Breach opened, where in December of 2016, we opened the New Breach on the causeway, and we just had massive amounts of water and salt being exported from south to the north for a sustained 8 to 9 month period. So we're seeing that shift in salt mass in the system. And then in 2021, our most recent condition, we can see we're drifting back toward the condition of higher salt mass in the South Arm, where it's, these dots are moving closer to the right. And now we're estimating we're around over 1,100 metric tons in the system. And if you want to toggle one more time, Ryan, just honing in, kind of zooming in on the 2021 conditions, we just continue to see increased mass in the South Arm. And we estimate that mass increases by about 40 to 50 megatons over the last year. And so next slide, it just shows this same idea in a slightly different way. So taking the concentrations of salt mass and the water volumes we have in the south arm, we're able to calculate the salt mass itself. So in the previous slide, we were showing a plot of concentrations and how that might relate to some theoretical mass. Here, we're actually estimating a mass in the south arm. So that's what's on the y-axis is salt mass in megatons. And this is calculated on a monthly basis. And then on the x-axis is time. And so we can see how that shifts through time. We can see there's been some variability. Again, decreases in salt mass, near in 2012, and then a huge drop after the new breach opens in 2017. So Ryan, if you want to just toggle one more time, kind of highlight those time periods. So kind of, a basic thing we've learned from this analysis and this exercise is the kind of the power of the system to export salt after certain hydrologic conditions. So after we have a huge snowmelt runoff or the lake is managed in a certain way, that is, a new breach is opened, we do see the situation where we're observing huge amounts of salt export from south to the north, which reduces the salt mass in the south arm, and it affects salinities. The other thing to really note here, though, is that from 2017 to the present time period, there's just been a gradual increase of salt mass over that 4 to 5 year time period. So he had that huge drop, and now we're starting to see it tick up. And this is kind of what's been on the radar of the Salinity Advisory Committee as they think about ways that the system could be managed or manipulated to try and help or amend this situation. But just so this group is aware, we've done this analysis. Again, it agrees well with what the Brine Shrimp Cooperative has done with their independent set of data and analyses. And this has been shared with the Salinity Advisory Committee. And what's concerning, I think, to that group is that the trajectory of the salt mass and the salinity and how it's been increasing steadily over the last few years. So I'll leave it at that. And if there's any questions, I'm happy to talk about this more. Yeah, Chris?
So I just want to get a little clarification on the relationship between the salt mass and salinity. It's like the salt mass is dropping, which is like just the absolute load of salt in the south arm, right? Mm-hmm. So just megatons of salt. So that's dropping due to the northward flow into the north arm of the lake that's actually exporting that salt. Mm-hmm. But then at the same time, because the lake level is so low, even though there's less salt in that south arm, the salinity is rising just because the less volume of water. Is that basically what's going on?
Yes, and I'd love to dig into that a little more, but you're right, it's this balance of we're losing water volume, so that should decrease our mass, but it's just, there's still so much salt mass coming in, and one way or another, that the salinities are still increasing, or we've observed that they've, as Ryan said, they're sort of kind of flattening now. But yeah, it's just this balance of water and salt mass, and we're in a condition where both are occurring, where salinity is going up and water volume is going down at the same time.
And so the reduced salt mass in the south arm, the concern about that is that not being able to maintain the salinity of the lake when the levels go back up. I'm trying to understand like the I guess especially biological difference between the two, because it seems like salinity is really going to be like the limiting factor biologically, like say for brine shrimp and maybe other organisms. But the salt mass, the concern about losing that salt mass is, I'm not quite sure I understand. I can't elucidate that. So
maybe I misspoke. I don't think there's a concern about losing salt mass to the north arm. Okay. The concern is that it's increasing in the south arm, and for exactly the reasons that you outlined.
The salt mass is increasing in the south arm, or the salinity?
Both. Yeah.
Both. Okay.
Both are. Okay. Yeah.
Okay.
But I think the analysis here was just to kind of identify this mechanism where we see these huge periods of export of salt to the north arm, either after a huge snowmelt runoff or after this kind of new breach, this new management paradigm where we had that new breach opening up.
Right. Okay.
And just being made aware of that.
Right. And just understanding how the clock works so that we can hopefully
Yeah.
keep it going in time. So yeah.
And it's an initial step to really get at a salt mass balance in the lake. Where is salt moving in the system? Where's it coming from? Where's it going? To also help inform, management of the system.
Okay. Great. Thank you.
I think it is important. This is a good topic. It's important to clarify this that the salt mass in megatons since 2018. If you look at, and that's this period here where I've got the pointer showing the black diamonds are salt mass. The salt mass in the south arm has continued to increase. It's been increasing since 2018, and most recently, we see a slight drop because we're exporting some salt to the north with some of these bigger inflows that we're having from the Bear River, etc. But the overall trend since 2018 is for increasing salt
mass. Okay.
in the south arm. So increasing concentration and increasing salt mass.
Okay.
And that seems a little bit counterintuitive to have increasing salt mass in the south arm at a time when the volume of water in the south arm has been shrinking and shrinking.
Right.
This is the big concern. Even the volume of water shrinking, the salt mass
is rising.
It continues to increase. That's a
so you're just stirring more spoonfuls of salt into your glass of water, basically.
There's more, yeah, exactly. There's more salt coming into the south arm than is leaving the south arm since 2018.
Okay, thank you. Appreciate that.
A question. This increase in salt mass in the south arm, at present, is that reflecting a recovery after the culvert closure?
I think that, that's been the idea, is that it's sort of returning to this precondition of when the culverts were closed, and back in 2016, it's kind of returning back to that condition. Because not only when we get we don't only get south to north flow through the causeway, we get north to south flow through the causeway. So we're importing a lot of salt there. And that is the idea. And that's been floated by the Salinity Advisory Group, is that there's sort of this conveyor belt where you have water moving from south to north, and it's sort of encouraging flow from north to south. And we know that the density and the salinity in the north arm is much greater. And so that we know that's a known source of salt import. We've done some preliminary work trying to quantify the flux at the new breach, trying to understand how much salt mass is exported to the north and how much is imported from the north. And we're getting some discrepancies there that we're still exploring. But you're right. I mean, it's sort of, the lake is mixing. The south arm is mixing with the north arm. And so intuitively, you kind of think that, the salt mass is going to increase in the south arm as a result.
So I'm just trying to clarify this. So in other words, we're going back to the pre-culvert closure condition, in which case then it is going to go back to that period's fluctuation with volume of the lake.
That's possible, yeah. I mean, I think it's important to consider that we're in a kind of a new paradigm now. The opening on the railroad causeway is different than it was in 2014 or 2016. I mean, the breach is much larger. It's in a different place, and I'm not sure we fully understand that it will behave like it did. I think it's kind of a new situation, and I'm not sure that that's been quantified well.
But Gary brings up a great point. We moved a ton of salt into the north arm when we opened the breach, a lot of salt, and it's coming back.
Mm-hmm.
And at a time when we have less water in this, we're bringing in less fresh water into the south arm, and yet we're bringing back a bunch of salt that we exported earlier.
Yeah,
It's what it is to the system, because everything's working to increase salinity.
Yeah, exactly. And if we go back to this salinity plot, the the high-end salinity value where brine shrimp are the happiest, as I understand it, is at about 160 grams per liter. And some of our more recent values, our most recent values, which are from November 30th, show that our upper brine layer, where the shrimp are, salinity is 166 grams per liter at 3510. And it's similar at 2565, by the way. So we're already at a point where we're, kind of getting out of the range where brine shrimp are happiest. And this gets back to why we want the lake to come up 4 feet or more if we're lucky. Because next October, late summer next year, we don't want to be, because we know we're going to see these salinities decline, but we look at the enormous increase in salinity we saw over this period, represented with this steep slope. And seasonally, this is a seasonal increase. We had a big increase in salinity this past season. The previous season, another big increase. We don't want to decline slightly and then have just another pretty significant increase in salinity. So I think everybody gets that. So pray for snow. I did not buy a ski pass this year, and so I'm taking credit for the great snowpack we're having. So I'm missing out on the skiing at a good cost. So you're welcome, everybody.
Go ahead, Thomas.
Yeah, just to reemphasize, I mean, our concern when we first wrote this data analysis to the Salt Advisory Committee is our concern was that we were actually seeing an increase in total salt load in the south arm of the lake at a time where we really didn't want to see that, Gary. The second point of our analysis was that having looked at the data prior to the breach opening, during the culvert closure, and then during the breach opening and after, we kind of thought that this information could be used ultimately to manage the system. If you look at it short term, you could say, okay, well, we could sort of dam it and let the head pressure or the head rise and then open up the breach and then actually export a certain amount of salt and try and time that with water inflows. And given, it would be a lot of work to do that, but the principle is that might be another management tool. In the long term, and I think Christine was pointing that out as well, is that what we're hoping is that we could get the breach to a certain level at lower lake levels where you would reduce or maybe eliminate even any return flow of the heavy brine. And then maybe at higher lake levels, you would still have some of that heavy brine come back to adjust for lower salinity. So that's kind of what we took away from that. And we were really happy when the USGS was able to sort of confirm with their data independently that, they saw sort of the same patterns that we were able to see.
I just want to caution something with this. What you're proposing is a valid management, technique, but it's going to be short term.
Yeah.
The problem is we still have to get more water in the lake.
Yeah.
And this can, under an immediate, a current extreme situation can be used, but that's not going to solve the problem for the lake in the long term unless we get water coming in.
Yeah. No, I would totally agree. And we need to get more water coming in. But if you look at the patterns over the last 100 years or so, you go through these wet cycles and drought cycles, and we don't know what's going to happen with global warming. Some of the data models are actually telling us we're going to see more precip in Utah. I don't know. I mean, it's not going to be in terms of snow. It's going to be probably rain. So, it'll be interesting to see how that affects the lake levels. But the idea, I think, in the long run is that throughout drought cycles or wet cycles, you can adjust your management system to try and maintain that salinity within an optimal range in the South Arm.
Again, I just want to caution, though, you're taking 100-year drought and wet cycles, but those hundreds of years of drought and wet cycles were not with us pulling water out of the system and increasing our demand on water in the system. So that is the ultimate challenge that we have to face to get water into the lake.
Yeah, No, you're preaching to the choir.
Okay, I just want to be sure because, you know, you don't want people to say that these are going to solve the long-term problem.
No, and I think there's a lot of positive happening in terms of water right now and trying to get more water to the lake and at the legislative level, at the, budgetary level as well. But, at the same time, right now, that's one lever that we can pull.
Right.
And for our SALT Advisory Committee, it's the only lever that we can pull right now. And so we're at least trying to get the maximum benefit out of that lever. I think that's the bottom line.
So Jake had a question. Jake, are you muted or?
Oh, his mic's not working. If you want, you can type it into the chat. Okay. Nothing. Oh, Lynn's wondering if this has impacts on mineral extraction operations.
I had a question.
Yes, Anne?
Sorry, so I'm just gonna address Anne's question. Took me a second to scroll up and see her question. So she asked, with the gauge data, can you see how diversions have been managed differently over time, possibly in response to the precip? We haven't done that detailed, we haven't done an analysis like that. The great news for the Bear River system, the Bear River Commission, they have a great website where they track diversions, etc., happening on the Bear River. So I encourage everybody to get familiar with that website. Just Google Bear River Commission. I think it's bearrivercommission.org or something like that. And then they show flows on the canals, etc., and then our main stem stream gauges. So a lot of work can be done on the Bear River for sure on getting at that, and potentially on the Weaver River as well. But we haven't done that yet.
Are there any questions that haven't been answered that were asked in the chat?
I don't think Jake ever was able to get. Did he get his question in there in the chat? I haven't seen it yet. Jake Sarago.
I don't see it.
Can you hear me now?
Oh, there you are. Hey, Jake.
Yeah, we can hear you.
Hey, yeah, I opted to figure out the microphone rather than type so much. I'm wondering, do we have time series of the weight of minerals extracted? And I understand that that's that the rates and efficiencies of mineral extraction depends on the lake level, but just curious about those those numbers relative to the influx of minerals, the ratio of minerals extracted from the inflows there, and whether if there's someone here from the mineral industry, or if, Ryan or Christine, if we have good numbers on, or any estimates on the amount of minerals extracted.
People have definitely thought about this in the past. Christine and I, more recently, have not done a deep dive into that. but it's definitely an area we're going to look into. And I know that Andrew Rupke and the Utah Geological Survey, they're great experts on what you're asking. So after this meeting, if you could ask those guys, and they'll probably have some good answers for you that I don't have right now. But we're hoping the data's there, and we think it is to kind of help with the salt mass balance question.
Okay, great. Thanks. Do you think it's an important component in the total balance?
I can't say right now, and
okay.
I'm ashamed to say that, I think Brian Loving delved into this potentially in his report in 2000. What year was that, Christine? 2002. And then the USGS did some reports in the mid 90s where I think they discussed this a little bit, this topic. I don't have the numbers in my mind here right now. I'm getting too old, so I'll have to answer your question later. Sorry.
Yeah, I had thought that. I mean, I could be completely wrong. I'm new to this world, but I had thought that the kind of common understanding was that overall mineral extraction, long-term mineral extraction, kind of balanced the inflow. But of course, there's the consequence of highly increased evaporation in order to attain that. But anyway.
And I think you're right. I've heard Corey Engeroth say that at previous TAG meetings, that the extraction roughly is equivalent to what was coming in from the inflows. But yeah, no, we're going to be delving a lot more into the salt mass balance question. That's kind of our focus right now. Actually.
I love salt mass balance, so can't wait to hear more.
Nice.
All right, any more questions for Ryan or Christine? All right, well, I'll let Ashley jump in. I'm not sure as far as our lunch goes, and I know you guys don't want to watch us eat, so we'll try to push through here. And I will mention while Ashley's putting up her presentation that you missed out, everyone missed out for not only lunch, but Ann Neville provided cookies for everyone. And you all bailed on it, so no cookies for any of you. It was Christmas cookies, specially wrapped, and so
I did want to watch you eat, though, John. I really did want to watch you eat.
Well, then you're going to get your wish. I can't wait to do that. That's one thing that I know I can do well.
I think Tim's getting
We're very
close.
skilled. Yeah.
Your encouragement for everyone to stay home is making a lot of sense now, John.
Yeah, huh? I wonder. Gee, a whole box of cookies. Who's going to get those?
I'll bring you some, Phil.
Can you guys see my screen?
Yes, ma'am.
Okay, thank you. Okay, this shouldn't. It's not. Okay. How do I make it in presentation mode on this screen? This one? What menu? I don't see a menu. Hold on, let me try this one more time. Present now. Window. This window. Is that better? Okay. Okay, this should go pretty quickly. I'm just going to go through some of the data from this year. So the dark black line on this graph is the overall average from 1999 to 2020. The red line is this year, 2021, and then all of the colorful lines are the past years, just so you can see the variation between years. Right now we're at about 7.8 degrees Celsius, so pretty warm. Obviously, we haven't taken the temperature today or yesterday, but I am assuming it's going to cool back down and hopefully get down to more normal temperatures. Like Ryan was saying, salinity is very high right now, so we use a refractometer on the surface. So the surface of the water right now is at an average about 17.1. Some sites are pretty high, almost 18%, but then we do have some sites near the inflows that bring down that average. It is one of the saltiest years we've seen so far, especially at this time right now. So for chlorophyll in the lake, we're doing all right. We're a little bit above average at 21.6 micrograms per liter. This year we started off pretty low and we had a big increase, and we saw it normalize luckily over the summer, but we did get really low, almost zero values again. So we are seeing chlorophyll reach very low levels in the summer. But luckily we have seen it pick back up. So we had a pretty weird year for our cyst densities in the lake, especially in September. We had a really high value. You can see that red line shoot way up. I had to change my y-axis a little bit so it was included in the entire thing. I think it was like around 420 cysts per liter as the density in September. And then we saw an immediate drop off. And now we're sitting right about average at 58.9 cysts per liter. Nauplii, we saw 2 generations. One was a little bit later than we thought, and then we did have another bump, probably because of the warm temperatures in September. We also had so many cysts in the lake that likely some of those hatched into Nauplii. And right now we're sitting at about 0.05 Nauplii per liter. Juveniles, even less. Same kind of bumps. We think maybe because the Nauplii peaked around late May, early June, and so did the juveniles, that maybe we missed a bump. We did see some weather that spring, which only allowed us to get out a little bit less than we're used to. So it's possible we missed a generation of Nauplii, and that is why the peaks are about the same time. So for adult shrimp, nothing too exciting. We're seeing less and less as the temperatures decrease, but I did want to point out that we had a pretty high year as far as females with cysts in September, and they are dropping below average right now. For total adults in the lake, we did also see that increase in September. So we just had a lot going on in the lake, a lot of productivity in September compared to the average. And that is all the data I have for you if you guys have any questions.
Make you go speed round now.
I gotta go fast.
Okay, if there's no questions, we're going to hand it over to Gary. Just grab your PowerPoint. Can you see his now? No.
I think you need to close yours.
I think I need to stop presenting for a second.
Yeah.
Okay. This. Does that show up now? Oh, nice. How about now? Okay. All right.
Is it working?
It's working.
Okay. Well, go over a few things from the sampling on the lake. First of all, Let's look at the phytoplankton. The chlorophyll in the lake doesn't look, the blue line for this year doesn't look that much different from the average of the last previous 5 years, except from the summer on. It's much lower on average from the summer, for the summer this year compared to past 5 years. If we look at the composition of the phytoplankton, we can see that there aren't any big differences. However, we do see that the bacillariophytes, the diatoms in particular, in summer were much lower than on average, and the cyanophytes were much lower on average than in previous 5 years. And that's because they don't do as well with the high salinity. So the high salinity was affecting the abundance of everything but the chlorophytes. Ashley went over the brine shrimp responses over this summer, or 2021. And the important thing here, and I think she pointed this out, is everything occurred later this year than in past years. And the number of females with cysts was much higher this year than in past years. So those were two really big differences that we see. The other thing that we see that's different is the amount of food. If the bottom, the figure in the bottom, chlorophyll per adult equivalent, if you look at over the summer, the amount of food per adult equivalent in the population, so that's the food per unit of biomass in the shrimp in the population, on average was much lower than in past years. And that may be explaining why we had so much cyst production rather than production by the females of live young, because they tend to produce cysts when food per individual has declined. So to summarize this year, we saw much less chlorophyll, much less phytoplankton during the summer months in the lake. There was less food per unit of biomass for the brine shrimp. And in response to that, that's one of the reasons why we saw so many females, more females producing cysts rather than producing live young. So we saw some big differences this year compared to the previous 5 years. Now, if you go to the top left-hand figure, which is cysts produced per liter, or cysts per liter in the lake versus the month, you can see there that that production by the females, focusing their reproduction more on cysts than live young, can be seen that there's more cysts per liter in the lake this year than in past years. And I'm going to cover or go over this a bit, because that figure of 400 cysts per liter in September is way, way high compared to what we might expect, given our information that we have on the brine shrimp in the lake. Okay, another thing that we finished since the August meeting is studies of food preferences by the brine shrimp at different age categories or developmental stages. And what we finished since August was looking at the bottom line, all three types of phytoplankton together, the Denaliella as the chlorophyte, Nitsia as a bacillariophyte, a diatom, and Euhalothaceae as the cyanophyte, the blue-green cyanobacteria. And you can see there that we have pretty good, both the adults and the juveniles preferentially are filtering out the chlorophytes out of the mixture. Secondly, they're taking out the diatom, the Nitsia, and they are showing the least preference for the Euhalothaceae, the cyanobacteria. So the adults and the juveniles are behaving similarly. The nauplii, on the other hand, are showing similar preference for the Denaliella and the cyanobacteria Euhalothaceae, and they showed they're avoiding taking in the diatoms. Well, the reason for this is the diatoms are too big for the nauplii to handle, and so they're not preferential feeding on them. Their preferential feeding on the cyanobacteria occurs primarily because they're small, and they can take them in along with the Donnelliella. So we now have, and we're preparing a manuscript for publication now, because there's no information out there on preferential feeding by Artemia on the natural foods. There's studies in the laboratory, one that we know of, that's looked at preferential feeding on various phytoplankton that they don't experience. Matter of fact, marine phytoplankton compared to Donnelliella. They did do Donnelliella in that study. In fact, there's very little preferential feeding in terms of any of the zooplankton out there. Most people assume that they take things in proportion to what's in the water column. And we're showing that they actually can preferentially take what's mixed up in a small volume of water. So this experiment has been completed, and we're in the process of writing this up. Okay, what I really want to focus on today is the progress that we've made in terms of the Great Salt Lake pelagic model, which has been our main focus for the last year. And this is showing where we are in terms of the pelagic model. And we are now moving into a stage where this is going to look much more complicated, because each of those boxes, phytoplankton, shrimp, and birds now, are going to have arrows going back to the abiotic, because we're now dealing with how each of the biological concepts of the lake are feeding back in terms of the nitrogen cycling in the lake. And so the model has to now bring feedbacks to that abiotic box that we have for that portion of the model. Okay, as of the August meeting, we discussed the idea that we had to get a better fit, the model to produce better on the phytoplankton subroutine. We saw some weaknesses there. And in the meeting in August, we discussed that the modifications needed to be brought in terms of the growth rates and allocation of the biomass of phytoplankton between the three different categories: chlorophytes, bacillariophytes, and the cyanophytes in the lake. And so that's where I did most of the modifications. And two modifications were applied, were included in the model. One was for the bacillariophytes and the cyanophytes. When we got cold water conditions, the model was saying they don't produce anything at all. And that's not true. And so what we did was to build into the model that at colder temperatures, it tailed off at some positive level of growth of those two categories of phytoplankton. It didn't go to zero. It asymptoted at some above zero level. So that was built in. The second thing that we built in was the allocation. And what the model now includes is that what amount of the resources, nutrients, nitrogen in the system that's not being used by the chlorophytes goes then to the cyanophytes, and what's not being used by the cyanophytes then goes to the bacillariophytes. So we have a priority of which one gets primary, secondary, and tertiary access to the nitrogen levels. And when that was built in, it didn't solve all the problems, but it did make things better. So the upper panel here that says previous deals with what I presented in August in terms of the chlorophyll A by month in the lake, the chlorophyte percentage of that chlorophyll by month for chlorophytes, percentage of cyanophytes, and percentage of bacillariophytes. And just as a sort of a quick reference here, if you see big differences in the bars between red and blue. Red is the observed values from the last 5 years, 2015 through 2020. Blue is what the model predicted. And if you go up to the scattered chart above it, you can see the correlation coefficient of fitting those numbers together. And you can see that chlorophyll was working pretty well, predicting. We discussed that in August. The chlorophytes were doing okay, not bad. The cyanophytes were doing okay and not bad. The bacillariophytes did terribly, an R of only 0.12. And if you look at the bar chart below, you can see that the numbers are way off, that the bacillariophytes were being predicted to be much higher than they really were observed to be. With these modifications, and you go down to the panel on the bottom, the light blue panel that says new, you can see that in making these changes, the chlorophyll value predictability went down a little bit. We lost some of the predictability there, but the apportionment between different categories went up tremendously, went up a little bit for chlorophytes, a little bit for cyanophytes, but it went up much better for the bacillariophytes. So the improvements there helped, but they're still not, for the bacillariophytes in particular, not satisfactory, in my opinion. The other problem that we can see with the model's prediction of the chlorophyll A by month is that the chlorophyll in the fall, October, November, and December, is not increasing fast enough. And I think there's a reason for this that I'm going to give. That's another modification we have to do. And let me point out, this model has become so large now that putting in any little modification like this means you have to go back and make sure that something else hasn't changed in the model that you didn't anticipate. So you have to go basically step by step through to verify things are still working right. So, oops, I'm not using my computer. Okay, if we look at 2021, the chlorophyll A prediction, given what we had of this summer, is not very good compared to looking at the last 5 years average. The cyanophyte breakdown is not far off. It's still pretty good at 0.65. The cyanophytes do great. The bacillariophytes do terribly. And even though the R value is very good, if you notice, it's a negative correlation. You want it to be a positive correlation. So your prediction from the model should be increasing when the observations increase. But in reality, they're going the wrong way. And that's because what happened, and I've checked this out, this is another modification that needs to be put into the model. The bacillariophytes are really much more sensitive to the increase in salinity, like we saw this year, than the cyanophytes are. And so we need to make that, build in that much greater allocation, so they're not picking up what the cyanophytes aren't using. That now has to be built in. They're not able to respond quickly enough at this higher salinity. So we know what's going on there, but let me just point out, neither the cyanophytes or the bacillariophytes are important food types in the recent years. The important thing is the chlorophytes. That's not the case, though, in the early years of this project when we had the blooms of the bacillariophytes and then blooms of cyanophytes as well. So it looks good for current years, but in past years, in those early, the mid-90s, the mid-1990s, yeah. It's not going to respond in the same way. Now, the real disappointing thing has to do with brine shrimp predictions. And cysts are great, so that the industry can do very well with the model predicting what cyst production is going to be. And I want to point out that the 2021 number there of 400 cysts per liter, which was observed by the state sampling. I'm concerned that that's an overestimate. And Thomas just gave me the figures for the industry for that time period, and it was 275 cysts per liter, and that would be much more in line with what the model is predicting. But the real weakness of the brine shrimp predictions is trying to predict each of the stages, the nauplii and the juvenile seen in the lake, does better with the adult number, but the predictions that we get are far off with the particular age categories in the model, and there's a reason for this. In terms of the biomass, it does pretty well, the total biomass of shrimp in the lake, but it doesn't break things down well between the age categories. And let me show you, just skip that, right? Show you two reasons why the shrimp model, the aspects of breaking down age structure in the predictions for the shrimp are off. And I mentioned this in August, and this needs to be now addressed in the model. The model is built in that a certain temperature is reached in the lake and the cysts hatch. And it's assumed all the cysts hatch on the same day. And that's not reality. And so what has to be built into the model now is a more complex allocation of the hatching of the cysts. And we have no particular empirical knowledge of what that's going to be. And what I'm going to do is a fix by just saying that 1 month in which the water temperatures become warm enough to start hatching the shrimp, the cysts, 1/4 of those cysts will hatch each week during that month. And the reason why this is so important is because by having the cysts all hatch at once, they totally deplete the phytoplankton, which means that the juveniles all starve to death. The juvenile then number will be underestimated. The nauplii number will be overestimated for that early time of the year. And then this carries on throughout the entire summer. And so the model has to somehow distribute that hatching of the cysts when the water temperature gets warm enough that it distributes the consumption of the phytoplankton more equally among age categories. Yeah, Thomas.
Gary, I think you may have to account for salinity in that hatchability as well, because of these higher salinity.
Salinity is built into it already.
Okay.
Okay.
Even at 170 parts per thousand.
The salinity comes in with that the proportion of those cysts that actually hatch at the time. It doesn't affect the date on which the hatching temperature affects that, but the proportion that are hatchable is affected by salinity.
Yeah, I wonder if inflow affects salinity as well, because at some salinity level, you're going to see much lower hatchability
Because they don't break diapause.
Yeah. Or no, even if they break diapause, but just the salinity being too high. And so at that point in time, I think it may be that just inflow of fresh water may be more important to the
To trigger it.
To trigger it.
Yeah, that's not built in right now. That may have to be built into in the future. We're trying to do one step at a time with this. But it's important, I think that's the important thing of trying to spread out when these nauplii appear from spring hatching, feed on the phytoplankton so they don't totally deplete it all at once, preventing any food for juveniles, and then that goes down the line.
So you're taking the month and you're equal 25% each
week during the month.
And what was the?
I have no better knowledge than anything to do than to spread it out that way. We don't have any of that information empirically.
Okay.
Yeah, you have to test it really.
Yeah,
I mean, we know that the hatching can be very slow.
right. It can be very, very slow. And what we've done in the laboratory, remember this model is totally built upon laboratory experiments. So we're not using the empirical observations from the lake to then test, to build the model and then use that to test the model. We're using the laboratory measurements on everything to build the model and then use that to test against the lake. So the two are independent of each other. Other than we know that something wrong is going on here now. And our hatching experiments that we've done with the cysts that are built into this model. We took the cysts and looked how many hatched over a 3-day period or something like that. And then we went back and froze them again, and then looked at them again 30 days later, froze those, looked at them again 30 days later. So we don't have that continuous time frame to be able to try to get at this.
So you can always change like 25 to whatever
Sure.
it ends up.
Yeah, I could.
matching
Yeah,
the
we
most.
could eventually go 75% in the first week, 10% in 15% in the next week, 5% and 5% or something like that. We can do that. Yeah.
It would seem like it'd be more of like a bell curve where you had a gradual then high.
It might be 25%, 50% and 25% in 3 weeks. Exactly. But what I'll do is I'll remake this model where we actually have a, like you said, a distribution of hatching. You can go in and change it. But we don't have that information right now. The other thing that needs to be changed, and this is far more difficult, is that temperature value, which sets off the hatching. And it does two things. It sets off the hatching and it sets off the death in the fall, the disappearance of the shrimp in the fall. And the way it's set up now is the model gets 12 months, 12 temperature values by the average value per month. And we know that that can't be the case because in some months the temperature changes dramatically from the first week to the last week, and in particular at times in the spring and times in the fall.
Like this month.
Yeah, like this month. And so that circle up there, which is the temperature input of 12 values, we don't have what the temperature value is at each week during the month, okay, in the lake. But what I need to do now is make that more complicated, which is, let's take, as an example, how to build this in. Let's take the average temperature of the month before and the average temperature for the current month and do an average between those two for the first 2 weeks of the month, and then take the temperature of the next month with the current temperatures and then do the average change for the next 2 weeks. So now you're getting a smooth curve, but you've got now a whole bunch more calculations that have to go in there. And in terms, everything, as any of you have done a computer model, there's counters in there that are doing time and other things. Now you can't have that counter dealing with temperature being the same as the counter that's going through on the week-by-week basis. So that's the next change that has to be built in. Finally, a lot of time has been put into the abiotic side, as I said, and that's building in the nitrogen budget that's being put in from the biology. Right now, the model is set up that there's a single base nitrogen value, and you're dividing that by the volume of the lake. Well, now we need to have the phytoplankton effect on it, the shrimp effect on it, and the bird effect on it. And that's what is over on the right side here. And what's on the right side is the addition that's gone into that abiotic module, that upper one there, in the flow of the model. And now each of those subroutines for phytoplankton, shrimp and birds has to feed back onto the abiotic, which isn't there now. And what's on the right side there is a conceptual flow chart of the model for each of the biotic effects. But that is simplified because now you have to put in each of the variables, each of the shrimp variables, Domplii, juveniles, adults. For the phytoplankton, you have to put in chlorophytes, the celeriophytes, cyanophytes. And you have to then put in how much did they grow during that time period, how much did they die during that time period. And each of those terms has to now go built into what's on the right side of the model. And what I thought was going to be an easy thing of just plugging this in, now you have to bring in all that information and link it to the other subroutines. And this is the sort of information that you need. We completed a run of brine shrimp body decomposition at different temperatures at a salinity of 120 ppt. And interestingly, I hadn't expected this, interestingly, the relationship is linear. That makes it easier to model than to have to build this as curves. And so what you can see is it's quite clear that as temperature increases, the decomposition rate is increasing. So that you can see at 10 degrees centigrade, 10% of the body only remains after 30 days. At 30 degrees centigrade, 23%. It takes 23 days for 10% to remain. So we've got this. We're going to run this at another salinity. We're not anticipating salinity is going to be really important on this. Temperature is going to be the major driving factor. So this is telling you your release of nitrogen that feeds back. An interesting sideline, not that it's important, we did a control bacteria in the lake and into just RO water from the lab. So it's doesn't have the lake bacteria in it, and it virtually made no difference in terms of the decomposition. And what that's telling us is that the shrimp body already has most of the bacteria already probably on the exoskeleton that's going to break down the body. It's already there. Now, we also need brine shrimp fecal pellets, an important thing to break down, and phytoplankton cells to break down. Unfortunately, we have been playing with these experiments, and they're not easy to do in brine. You can't use the methods that people have used for freshwater to just use in the brine. First of all, when you pass through the pellets or the phytoplankton cells through a filter to get the weight of them at different time periods to see the decomposition, lo and behold, the salt precipitates on the filter. So what we have to do now is in the extraction or in the process, we didn't know this, we saw all of a sudden huge increases in the amount that was there. And that can't be, it's dead, it should be decomposing. You have to go through and rinse it with RO water to get the salts out of the filter paper before you can dry it and weigh it. So that adds an extra step, couple steps, because we do it twice to get that. The second thing was the phytoplankton cells. We tried to kill them by freezing. It didn't work. It turns out that the freezing didn't kill the phytoplankton, and they actually grew in the decomposition experiment, so we got more phytoplankton at the end of the experiment than at the beginning. Brine shrimp fecal pellets showed the same thing because they're not able to digest a lot of the phytoplankton. And so lo and behold, the phytoplankton that were on the fecal pellets after we froze them, all of a sudden started growing again. So we got an increase in mass, not a decrease in mass. So the next step is, instead of using freezing as a way of trying to kill things, we're going to microwave everything.
Nice.
And as of today, we got a new microwave because the old one had blown up in the lab. Actually burnt up. And so that's the next step. We can't put them through the autoclave because that would be far too harsh and would break everything apart and you wouldn't get any decent measurements. So we're going to try microwaving now as a means of killing everything. But salt has been a problem and killing these things has been a problem. Okay, last thing has to do with the GIS analysis. All the data since 1994 has been entered and the quality control work, QC, QA, has pretty much been completed. We're in the process now of getting all the data in from 2020 to 2021. Then that's going to have to be quality controlled. And then I need that data for 2021, most recent data for each site and each month. And then after the new year, we're going to sit down with our GIS specialist and start looking at maps and seeing what comes out that looks really potentially interesting. The one thing we did have to do, as I pointed out in August, as an example, on the left-hand side is if we include all the weather data from HAT and other weather stations on the lake, there's very little wind speed out on the lake, which we know is not true. And that's the reason why those weather stations, the reason for that is those weather stations go down when there's high wind speeds. So if you use just the weather station at the airport and on land at various airports and places, it gives you a far better picture of what the wind speeds are on the lake.
Do you think the causeway breach will confound any of that?
That's something we can look at. So in other words, this is these plots here are wind speeds versus where cysts are found. Okay, concentration of cysts on a lake. Well, we could easily look at where those patterns against wind when the causeway, the breach was closed, those years. And then we can compare that to when the breach was open, both before and after, with wind being included. So those things can be analyzed once we have all this together. So that's all I have. Questions?
I was wondering, when you look at the different kinds of phytoplankton, is that set up as a proportion? So if they eat 80%, then the rest goes down?
No.
No? Okay.
It's built up by how much you started with, and then you've got a control, which measures with no shrimp in it, which measures how much each of those grew or declined over the 1 hour period of the experiment.
Okay.
Okay, so you then take what you started with in the experiment, increase it or decrease it by the amount that the control tells you, suggests, and then you compare that at the end versus what you started with at the beginning.
Okay.
And see which one tended to decrease more than the other ones.
Okay.
It is all in terms of proportional changes. So,
Okay.
but it's in proportion to what you started with.
Gotcha. Not just like out of 100.
No, it's not looking at
Okay.
everything has to add to 100. Right?
Okay.
And we can go back in those experiments and actually calculate how much was absolutely consumed.
Okay.
But absolute consumption, if you started with very little, you're going to have very little, you're going to have less absolutely eaten, right?
True.
And so you can't just go by how much was reduced, because it's the reduction relative to what you started with. Okay?
Yeah.
Any questions?
Anybody else have any questions? You guys are all hungry too?
Yeah.
Did we lose everyone?
Yeah, I'm sorry.
All right, well then, quickly, I'm just gonna throw out some dates